Enthalpy of atomization. Consider the following example of atomization of dihydrogen. You can see that H bonds are formed by the breaking of HH bonds in dihydrogen. The enthalpy change in the process is known as enthalpy of atomization. It is the enthalpy change on breaking one mole of bonds completely to obtain atoms in the gas phase. In case of diatomic molecules like dihydrogen, the enthalpy of atomization is also called the bond dissociation enthalpy. Note that the products are the only atoms of carbon and H in the gaseous phase. Now see the following reaction in which Na gives Na which is in gas form. In case the enthalpy of atomization is same as the enthalpy of sublimation, bond enthalpy. Chemical reaction involves the breaking and making of chemical bonds. Energy is required to break a bond and energy is released when bond is formed. It is possible to relate heat of reaction to change in energy associated with breaking and making of chemical bonds. With reference to the enthalpy, changes associated with chemical bonds, two different terms are used in thermodynamics. First, bond dissociation enthalpy and second is mean bond enthalpy. Let us discuss these terms with reference to diatomic and polyatomic molecules. Diatomic molecules consider the following process in which the bonds in one mole of dihydrogen are broken. H2 gives H in the heat of enthalpy. The enthalpy change involved in the process is the dissociation enthalpy of HH bond. The bond dissociation enthalpy is the change in the enthalpy when one mole of covalent bond of gaseous covalent compound is broken to product form in the gas phase. In the case of polyatomic molecules, the bond dissociation energy is different for different bonds within the same molecule. Polyatomic molecules. Now, us consider a polyatomic molecule like methane CH4. The overall thermochemical equation for its atomization reaction is given CH4. Further reaction gives carbon plus 4 hydrogen. In methane, all the 4 CH bonds are identical in the bond length and energy. However, the energy is required to break the individual CH bonds is called successive step differ. We find that the CH bond enthalpy in methane is 416 kJ per mole. It has been found that mean CH bond enthalpies differ slightly from compound to compound as CH3, CH2Cl and CH3NO2 etc. but it does not differ in the great deal. However, using the Hess law, bond enthalpies can be calculated. Bond enthalpy values of some single and multiple bonds are given in the table. The reaction enthalpies are very important quantities as there is arise from the change that accompany the breaking of old bonds in the formation of new bonds. We can predict enthalpy of reaction of gas phase if we know different bond enthalpies, the standard enthalpy of the reaction is related to the bond enthalpies of the reactions and the products in the gas phase reactions. The relationship is particularly more useful than the required values are not available. The net enthalpy change of the reaction is the amount of energy required to break all the bonds in the reactant molecules minus the amount of energy required to break all the bonds in the product molecules. Remember that there is a relationship is approximate and valid when all the substances in the reaction is in the gas state. Lattice enthalpy. The lattice enthalpy of an ionic compound is the enthalpy change occurs when one mole of ionic compound dissociate into the ions in the gaseous state. Since it is impossible to determine the lattice enthalpies directly by the experiment, we can use indirect method where we construct an enthalpy diagram called Born-Haber cycle. Now, let us calculate the lattice enthalpy of NaCl by the following reactions. Enthalpy of solution. Enthalpy of solution of a substance is the enthalpy change when one mole of it dissolves in a specific amount of solvent. The enthalpy of the solution at infinite dilution is the enthalpy change observed on dissolving the substance in an infinite amount of the solvent, when interaction between the ions are negligible. When an ionic compound dissolves in a solvent, the ion leaves their ordered position on the crystal lattice. They are now more free in the solution, but solvation of these ions also occur at the same time. This is shown diagrammatically for an ionic compound. The enthalpy of solution of AB in water is therefore determined by the solution of selective values of lattice enthalpy and enthalpy of hydration of ions. For most of the ionic compounds, delta solution H negative is positive and the dissociation process is endothermic. Therefore, the stability of the most salts in the water increase with rise in temperature. If the lattice enthalpy is very high, the dilution dissolution of the compound may not take place at all. Why do many fluorides tend to be less soluble than the corresponding chlorides? Estimates of the magnitude of the enthalpy changes may be made by using tables of bond enthalpies and lattice energies. Enthalpy of dilution. It is known that the enthalpy of solution is the enthalpy change associated with the addition of specific amount of solute to the specified amount of solvent at a constant pressure and a temperature. This argument can be applied to any solvent with slight modification. Enthalpy change for dissolving 1 mole of gaseous hydrogen chloride into 10 mole of water can be represented in the reactions. The value of delta H show general dependence on the enthalpy of the solution on amount of solvent. As more and more solvent is used, the enthalpy of solution approaches a limiting value, that is, the value in infinite dilating solution. For hydrochloric acid, the value of delta H is given. Spontaneity. The first law of thermodynamics tells us about the relationship between the heat absorbed and the work performed or on by the system. It puts no restriction on the direction of heat flow. However, the flow of heat is unidirectional from higher temperature to lower temperature. In fact, all naturally occurring processes, whether chemical or physical, will tend to produce spontaneously in one direction only. For example, a gas expanded to fill the available volume, burning carbon in dioxygen, giving carbon dioxide. But the heat will not flow from colder body to warmer body on its own. The gas in the container will not spontaneously contract into two corners, or carbon dioxide will not form carbon or dioxygen spontaneously. These are many other spontaneously occurring changes, slow and unidirectional change. This is what is driving force of spontaneously occur changes. What determines in the direction of a spontaneous change? In this section, we shall establish some criterion for those processes, whether these will take place or not. Let us understand what do you mean by spontaneous reaction or change. You may think by common observation that spontaneous reaction is one which occurs immediately when contact is made between the reactions. Take the case of combination of hydrogen and oxygen. These gases may be mixed at room temperature and left for many years without observing any perceptible change. Although the reaction is taking place between them, it is an extremely slow rate. It is still called a spontaneous reaction. So spontaneity means having the potential to proceed without the assistance of any external agency. However, it does not tell about the rate of reaction or process. Another aspect of spontaneous reaction or process, as we see, is that we cannot reverse their direction on their own. We may summarize it as follows. A spontaneous process is an irreversible process or may only reversed by some external agency. Is decrease in enthalpy a criterion for spontaneity? If we examine the phenomenon like flow of water downhill or fall of a stone on the ground, we find that there is a net decrease in the potential energy in the direction of the change. By analogy, we may be tempted to state that a chemical reaction is spontaneous in a given direction because decrease in energy has taken place, as in case of an exothermic reaction. The decrease in enthalpy is passing from reactant to product may be shown for any exothermic reaction on an enthalpy diagram. Thus, the postulate that driving force for a chemical reaction may due to decrease in the energy sounds reasonable on the basis of evidence so far. B. Entropy and spontaneity. Then, what drives the spontaneous process in a given direction? Let us examine such a case in which delta H is equal to 0. That is, there is no change in enthalpy, but still the process is spontaneous. Let us consider diffusion of two gases into each other in a closed container, which is isolated from the surrounding as shown. The two gases, say gas A and gas B, are represented by black dots and white dots, respectively, and separated by a movable partition. When the partition is drawn, the gases begin to diffuse into each other, and after a period of time, diffusion will be complete. Let us examine the process before the partition. If we were to pick up the gas molecules from left container, we should be sure that these will be molecules of gas A, and similarly, if we were to pick up and the gas molecules from right container, we should be sure that these were molecules of the gas B. But if we were to pick up molecules from the container when partition is removed, we were not sure whether the molecules picked are of gas A or gas B. We say that the system has become less predictable or more chaotic. We may now formulate another postulate. In an isolated system, there is always a tendency for the system's energy to become more disordered or chaotic, and this could be a criterion for spontaneous change. At this point, we introduce another thermodynamic function, entropy, denoted by S. The above-mentioned disorder is the manifestation of entropy. To form a picture, one can think of entropy as a measure of degree of randomness of a disorder in the system. The greater the disorder in an isolated system, the higher is the entropy. As far as the chemical reaction is concerned, this entropy change can be attributed to the rearrangement of atoms or ions from one pattern in the reactants to another. If the structure of the products is very much disordered than the reactants, there will be resultant increase in entropy. The change in entropy accompanying a chemical reaction may be estimated quantitatively by a consideration of structure of the species taking part in the reaction. Decrease of regularity in the structure would mean increase in entropy. For a given substance, the crystalline solid is state of lowest entropy. The gaseous state is the state of highest entropy. Now let us try to quantify entropy. One way to calculate the degree of disorder or chaotic distribution of energy among molecules would be through statistical method, which is beyond the scope of this statement. Other way to be related to this process to take heat involved in the process, which could make entropy a thermodynamic concept. Entropy, like any other thermodynamic property such as internal and the enthalpy, is the state function, and delta S is independent of path. Whenever heat is added to the system, it increases molecular motions, causing increased randomness in the surrounding. Thus, heat has randomizing influence on the system. Can we equate delta S with Q? Wait. Experience suggests us about the distribution of heat also depends on the temperature at which heat is added to the system. A system at higher temperature has greater randomness in it and has one at lower temperature. Thus, temperature is the measure of average chaotic motion of particles in the system. Heat added to a system at lower temperature causes greater randomness than when the same quantity of heat is added to it at a higher temperature. This suggests that the entropy change is inversely proportional to the temperature. Delta S is related with Q and T for a reversible C. Gives energy and spontaneity. We have seen that for a system, it is total entropy change, delta S total, which decides the spontaneity of the process. But most of the chemical reactions fall into the category of either closed system or open system. Therefore, most of the chemical reactions, these are changes in both enthalpy and entropy. It is clear from the discussion in the previous section that neither decrease in enthalpy or nor increase in entropy alone can determine the direction of spontaneous change for these systems. Thus, Gibbs energy change is equal to enthalpy change, which is equal to temperature into entropy change, and it is referred to the Gibbs equation, one of the most important equations in chemistry. Here we consider both terms together for spontaneity, energy, and entropy. As indicated earlier, dimensionally, if we analyze, we find that delta G has units of energy because both delta H and the delta Ts are energy terms. Now let us consider how delta G, which gives energy, is related to the reaction spontaneity. Note, if a reaction has positive enthalpy change and positive entropic change, it can be spontaneous when delta Ts is large enough to outweigh delta H. This can happen in two ways. A positive small entropic change of the system can be small, in which case delta T must be large. The positive entropy change of the system can be large in case T may be small. The former is one of the reasons why reactions are often carried out at high temperature. The entropy and second law of thermodynamics. We know that for the isolated system, the change in the energy remains constant. Therefore, increase in entropy in such systems is the natural direction of spontaneous change. This is the second law of thermodynamics. Like first law of thermodynamics, second law can also be stated in several ways. The second law of thermodynamics explains why spontaneous exothermic reactions are so common. In these exothermic reactions, heat released by the reaction increases the disorder of the surroundings and overall entropy change is positive, which makes the reaction spontaneous. Absolute and third law of thermodynamics. Molecules of a substance may move in a straight line in any direction. They may be spin like a top, and the bonds in the molecules can stretch and compress. These motions of the molecules are called translational, rotational, and vibrational motion respectively. When temperature of the system rises, these motions become more vigorous and entropy increases. On the other hand, when temperature is lower, the entropy decreases. The entropy of any pure crystalline substance approaches to zero as the temperature approaches absolute zero. This is called the third law of thermodynamics. This is so stated because there is a perfect order in the crystallization at absolute zero. The statement is confined to pure crystalline solids because theoretical arguments and practical evidences have shown that entropy of solutions and supercooled liquids is not zero at 0 Kelvin. The importance of the third law never lies in the fact that it permits the calculation of the absolute values of entropy of pure substance from thermal data alone. Gibbs energy change and equilibrium. We have seen how a knowledge of the sign and the magnitude of free energy change of chemical reaction allows prediction of spontaneity of the chemical reaction, prediction of useful work that could be extracted from it. So far, we have considered free energy changes in irreversible reactions. Let us now examine the free energy changes in reversible reaction. Reversible, under strict thermodynamic sense, is a special way of carried out a process such that system is that all surroundings. When applied to a chemical reaction, the term reversible indicates that a given reaction can proceed in either direction simultaneously, so that a thermodynamic is set up. This means that the reaction in both the direction should be proceed with a decrease in free energy, which seems impossible. It is possible only if at the equilibrium the free energy of the system is minimum. If it is not, the system would spontaneously change to configuration of the lower free energy. Gives free energy for a reaction in which all reactants and products are in standard state. Delta Rg is related to the equilibrium constant. For strongly endothermic reactions, the value of delta Rh negative may be large and positive. In such a case, the value of K will be much smaller than 1 and the reactions is unlikely to form much product. In case of exothermic reaction, delta Rh negative is large and negative, and delta Rg is likely to be large and negative too. In such cases, K will be much larger than 1. We may expect strongly exothermic reaction to have large K and hence can go near completion. Delta Rg also depends upon delta Rs. If the changes in the entropy of reaction is also taken into the account, the value of K or extent of chemical reaction will also be effective depending upon the whether delta Rs is positive or negative. It is possible to obtain an estimation of delta G negative from the measurement of delta H negative and S negative Then calculate K at any temperature for economical yields at the products. If K is measured directly into the laboratory, value for delta G negative at any other temperature can be calculated by using equation 5.24. So here our chapter ends. Now let us remind its summary. Thermodynamics deals with the energy changes in the chemical or the physical processes and enable us to study these changes quantitatively and to make useful predictions. For these purposes, we can divide the universe into the system and the surrounding. The chemical of the physical process lead to the evolution of absorption of heat, part of which may be converted into work. These quantities are related from the first law of thermodynamics. Change in internal energy depends upon not on the state functions, on initial and the final state only in a state function where Q and W depends on the path, not on the state functions. We follow sign convention of Q and W by giving positive sign to these quantities, which are these added to the system. We can measure the transfer of the heat from one system to another, which causes the change in the temperature. The magnitude of rise in the temperature depends on the heat capacity of the substance. Therefore, heat absorbed or evolved is Q is equal to C delta T. Work can be measured by W is equal to minus PEX delta V. In case of expansion of gases, under reversible process, we can put for infinitesimal changes in the volume making. In this condition, we can use the gas equation P is equal to nRT. At constant volume, W is equal to 0, then delta U is equal to QV. Heat transfer at constant volume, but in study of chemical reaction, we usually have constant pressure. We define another state function enthalpy change, can found directly from the heat at constant pressure. These are the varieties of enthalpy changes to phase such as melting, vaporization and sublimation. Usually occur at constant temperature and can be characterized by enthalpy, which are always positive. The enthalpy of formation, combustion and other enthalpy charges can be calculated using Hell's law. First law of thermodynamics does not guide about the direction or the chemical reactions. What is the driving force of chemical reaction? For isolated system, we define another state function as entropy for this purpose. Entropy is measure of disorder of randomness. For spontaneous reaction, total energy change is positive. Therefore, an isolated system, so entropy change distinguishes a spontaneous change while energy changes does not. Entropy changes can be measured by the equation. Chemical reactions are generally carried out at constant pressure, so we can define another state function gives energy G, which is related to the entropy and enthalpy changes of the system by the equation. For spontaneous change and at equilibrium, standard Gibbs energy change is related to the equilibrium constant. K can be calculated from this equation if we know delta G, and which can be found from this equation. Temperature is an important factor in the equation. Many reactions which are non-spontaneous at low temperature are made spontaneous at high temperature for the system having positive entropy of the reaction. So these are the exercises question. That's it. Thank you.